Now we derive the formula. So this is our formula, the whole formula here. Okay, yeah. All right. In this formula, n is the variable, n, variable. Yeah. P is the constant. P should be given. P is a known constant. Yeah. All right, between 0 and 1. P. So usually when we write a representation, so we want to represent the terms based on the variable. Based on the variable. Yeah. So usually we want to write our terms based on the variable. Each term is represent around that variable. Okay, yeah. So here, variable is n. We need to look at what is the coefficient of this variable n. Yeah. Consider that. So n is the variable, but we want to see what is the coefficient, right? So n, this first term, it contributes the coefficient 1/2 p, right? P over 2. The first term, because this plus 1 does not contribute a coefficient, right? Yeah, this n 1/2 times n times p. So the coefficient part is p over 2. Okay, all right. The second term, the contribution on the coefficient, this whole parenthesis, right? This whole parenthesis is the contribution of the coefficient, plus 1 minus p. Then, the whole parenthesis, that's the coefficient of the n. Okay, all right. After that, next term, the constant term. Okay. No variable. Okay. So variable we represent the first term. The second term, no variable, right? Yeah. Yeah. So only one term left. P over 2. P over 2. So the first term can be simplified, right? First term. Yeah. P over 2 plus 1 minus P. After simplification, we get 1 minus P over 2. 1 minus P over 2 after simplification. Yeah. Yeah. So after simplification, we get this term. Okay? All right. Then, next, I talk about approximation, because in our computer science, we do approximation a lot. And many times, in order to make our computation as simple as possible, we want to use the simpler formula that approximates the original formula, All right. So here, let me do one simplification, one approximation. I only take the first term. I ignore the second term. P over 2, because very small, right? P is between 0 and 1. P over 2, a very small number, okay? A number between 0 and 1/2. Between 0 and 1/2. Think about, when n is large, if we ignore 1/2, is it a big deal? No, right? So, very small. But if we ignore that term, we get a simpler formula, right? Yeah. So we get a simpler formula. And here, this, after simplification, approximation, yeah. So this term, we call it the dominant term in the original formula, because this term dominates all the other terms. Okay? Dominates. Yeah. But the question, how to explain how to explain that dominance? How this term dominates other terms? So later we will see. Yeah. Because when n is very large, all the other terms, if you look at the ratio, all the other terms, if you look at the ratio with this dominant term, that ratio is very small. The ratio will be close to 0. How about that? You look at this term, p over 2. If you use p over 2 to take the ratio with the first term, that ratio, when n is very large, that ratio very small, right? Close to 0. Very close to 0. Can we say the first term dominates the second term? Yeah. And sometimes our formula, we may have several terms. If we just take the leading term, and we can say the leading term dominates all the other terms. So that's the reason we have this concept, the dominant term. And when we take approximation, we only take that leading term. Because other terms, yeah, so here. Let me give you a concrete example. If I have 0.5 n cubed, then plus 10n squared, plus 20n plus 30. Okay? Yeah, suppose we have this formula. Okay? Now, you know, the first term is the leading term, right? The first term is the leading term. Yeah. Now here we want to say when n is very large, the first term dominates all the other terms. Can you see that? The first term dominates all the other terms. Yeah. How do you see that? Can you use the second term over the first term? Look at the ratio. When n is very large, is it a very small number? Second term over first term. Okay? Second term over first term, if I, n squared over 0.5 n cubed. After simplification equals 20 over n, right? When n is very large, is this approaches 0? 20 over n. N is very large. You can see how the first term dominates the second term. Similarly, you can see the first term dominates the third term, and the first term dominates the last term. That's why we call the leading term the dominant term. Yeah. And if the first term dominates all the other, can we ignore all the other terms? We only use the first term as the approximation of the whole formula. How about that? When n is large. Do you feel it's a good approximation? Do you feel comfortable ignoring all the minor terms? We just take the dominant term and ignore all the other terms, minor terms. Yeah. First term, major terms. Yeah, because remember, I said the last time, I said, we only worry about the situation when n is large, right? When n relatively small, we don't worry. When n is relatively small, because our computer is very powerful. Okay? Our computer can handle relatively small n easily. Yeah. But it is very hard to do the calculation when n is very large. Right? Yeah. So we worry about very large n. Yeah. But when n is very large, if you look at the ratio, all the other terms, comparing with the dominant term, that ratio very, very small, right? Close to 0. That's the reason we can ignore those minor terms. Okay, so here I want to say this. When we do simplification, just take the first term, leading term. Because much simpler, right? When we work on the leading term, it's dominant, dominates all the other terms. Yeah. So we're fine. We have good approximation. Yeah. We treat. Yeah. We have the good approximation. Yeah. All right. So that's the first, concept I want to introduce. All right. So the dominant term gives a good approximation. Okay. Yeah. The minor terms can be ignored without significant loss. Yeah. If you look at the ratio when n is large, that loss, tiny loss, that loss, very small. Yeah. So, all right, so then, because later we will use this way a lot. Okay. Yeah. All right. Yeah. So we finish that topic. Okay. Yeah. Average. Yeah. So that average topic. C.2 actually. Yeah. Now C.3. Repeated squaring technique. I show you one example before, but this place I want to explore this technique. Yeah. Repeated squaring technique. So we keep doing square operations. Okay? Square, second square, third square. We keep doing squares to make our monomial evaluation more efficient. That's the idea. Yeah. How do we apply the squaring operation to calculate the monomial? So here the goal, this technique is for monomial. What's the monomial? X to the kth, or x to the n, yeah. K or n. Yeah. All right, monomial. Yeah. So here we want to do this. How to use the minimum number of multiplications to calculate the monomial. Okay, calculate the monomial with the minimum number of multiplication. So do you have idea? Yeah. Yeah. We only calculate that monomial. Okay? You do not need to calculate polynomial. One term. And you do not look at the coefficient. The coefficient is 1. Yeah. But how do you, we know, when we use the square operation, we can do faster. The question, how do we apply the square operation to minimize the number of multiplications in that calculation? That's the question. Okay, all right. So here, let me show you some discussion first. All right. Yeah. So that's our sub-question. So here I do not list it as a main question. So I do not use question number because it's a small question. So I do not use a new question number here. All right. Yeah. Yeah. So then, so here some discussion. All right. Yeah. In the Horner's rule, remember, in the Horner's rule is applied on polynomial. It's not a monomial. Okay. Yeah. If you apply Horner's rule on monomial, you may not get an efficient solution. You may not get a good solution. Yeah. On monomial. Yeah. And but for the polynomial, yeah. For the polynomial especially, the coefficients are given in an arbitrary way. The coefficients, there is no pattern in the coefficients, no pattern, arbitrarily given. all the coefficients. Here the pattern, later in our topic, our fifth topic, C.5, I will talk about that special pattern. Here we assume there is no specific pattern for the coefficients. In this situation, the Horner's rule gives us the best solution. Best solution. Okay? Yeah. All right. Yeah. Yeah. But then the next question. There are some special situations. There are some special situations. If you apply Horner's rule, you may not get a best solution. Or in other words, you can do much better in certain special cases, better than Horner's rule. You can do much better than Horner's rule in some special cases. Yeah. So here I'll use 3 topics to show you those 3 special cases. We can do better than Horner's rule. Okay? All right. Yeah. 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 So now let's consider our first special case. Yeah. All right. X to the 4th, I gave you this example before. Yeah. So we use 2 multiplication because we do square operation twice, right? Yeah. Square. 1 square operation, you do 1 multiplication. You do twice, so you need 2 multiplications. Yeah. All right. Let's continue. Keep doing square operation. Yeah. All right. Yeah. The first, second, 2 square operations. Yeah. All right. So here we cut, repeated square. Yeah. Then, this time we consider n. The n is power of 2. How about that? Yeah. N is a special case. N happens to be power of 2. Can you see how many squares do we need? Square operations do we need to calculate x to the nth power? Where n equals 2 to the k, that special number, power of 2 number. We can use induction, we can use experiments, induction, to see the rule. Yeah. So what's that rule? Yeah. Let's do experiments. Yeah. All right. Yeah. So we do a chart here. K column, yeah, because your n equal to the k could be 1, 2, 3, 4, right? Yeah. K. We choose k, 1, 2, 3, 4, and so on. All right. X to the n, how many multiplications we need to calculate x to the n? Number of multiplications. Yeah. All right. When k equals 1, 2 square, 1 multiplication, right? Yeah. Because we need to calculate 2 square. The exponent is 2 to the 1st. So 2 square, 1 multiplication. When k equals 2, the exponent is 4, 2 to the 4th. You need 2 multiplication, right? When k equals 3, exponent is 2 to the 3rd. That's 8. You need how many multiplications?
You need
3. Yeah, because 1 more, right? After you get a 2 to the 4th, you just do another square operation. You get that. Yeah. When you keep doing square operations like this, do you get an idea when you have a general k, we need to calculate x to the 2 to the kth. How many multiplications? Yes, that's by the induction, because we can see the rule easily, right? Yeah. So you have k multiplications. All right. Then conclusion. conclusion. Okay, all right. Yeah. Here you can see if k equals 10, how many multiplications do you need? When k equals 10, n equals 1024. When you calculate x to the 1024, you need 10 multiplications, right? You need 10. Yeah. So here you can see how much is the improvement. How much is the improvement? You reduce the multiplication number. Yeah. Think about it. If you use Horner's rule. If you use Horner's rule to calculate this monomial, how many multiplications do you need? Horner's rule. Calculate this monomial. If you Horner's rule. Coefficient is 1, so you do not need to multiply that coefficient. Coefficient is 1. How many multiplications do you need? Horner's rule. Horner's rule. Horner's rule, the multiplication. Number one, 112? Oh, 512. He said 512. Just divided by 2. This number divided by 2. Horner's rule. Horner's rule. Oh, yeah. Let me ask you this question. Yeah. We do Horner's rule on this polynomial. How many multiplication do you need? N. Great. N. Yeah. But this time our N is 1024, right? By Horner's rule, that means should be this N, but the good thing is because we do not need this coefficient multiplication, right? So that means we can save one multiplication, right? If you save one multiplication, your number is 1023. If you use Horner's rule, you need this number, 1023. Because Horner's rule, you do not apply square operation. No square operation in Horner's rule. Okay? Yeah, that's why you do not use square operation. So that's 1023. Now, look at the improvement. If you, by repeated squaring against Horner's rule, you reduce the number of multiplication from 1023 to 10. Is that improvement big? Yes. So you know, that improvement is big, right? Yeah. Now, do you remember our last question in quiz 1? I give you the quiz 1. Last question. Do you remember that question? Yeah. Let me show you. Yeah, because in my screen, I just show you the last question in quiz 1 related to this topic. All right, let me show you. Quizzes. Number 1. Okay, all right. Preview. All right, yeah. Let's go to the last question. All right. Can you see that? Yeah. Yeah. Oh, too small. Yeah, last one. I remember. Let me enlarge. Okay, make sure you can see it. All right, this big. Right? Yeah. If you want to look at your laptop, it's okay. Yeah. All right. Is it possible that one can find a special polynomial with n terms? Yeah. Special polynomial with n terms. Imagine that n is a very large number, such that the value of this polynomial can be calculated with less than 0.01% of n multiplications. Think about that. Yeah. the the saving is huge, right? Saving is huge. No. So here, yeah, I connect to, this last question, connect to our current discussion. Yeah. All right, current discussion. All right, let me jump back to the current discussion. All right, here you can see we reduce from 1023 to 10. When we increase that K, can we reduce more? Here our K is 10, right? If we increase to 100, can we reduce much, much more? Yeah, right? Yeah. So here you can see when we do things like this, we have confidence because reduce from n, the multiplication from n to 0.01% of n. The question, is it possible? Is this example, from this example, we can see it's possible, right? This huge reduction is possible, right? Yeah. But there is only one missing piece. There is one missing piece here. Yeah. So you cannot use this example to answer our question number 10 in quiz 1 directly because the condition does not match. You need to go back to look at the condition carefully. The condition here, there is a special polynomial with n terms. Our monomial only has one term, right? So we need a polynomial with n terms. You can use special polynomial. You're allowed to use a special polynomial. But that polynomial, you need to make sure that polynomial has n terms. Okay? Yeah. But you can still use this 0.01% of n multiplications to find its value. Okay? So here we have one missing piece in the puzzle. Okay? So this final puzzle, we have one missing piece. Missing piece. Near the end of the class, you will have that missing piece. Okay? You will have that missing piece. All right, let's continue. All right, so here. So your knowledge here, okay? Yeah. Huge improvement. All right, yeah, huge improvement. All right, all right. Yeah. Essence of this method. We use the resource as much as we can to save operations. So here, why we can save so much, so computing time, let's say computing operations. Yeah. Operations, that's resource, right? Computing operations we treat as resource. Yeah. All right, yeah. So here, the reason, let me explain this resource understanding. Saving resource, that understanding. All right. When we apply our first multiplication to calculate x squared, then x squared becomes our resource, right? Why? Because x squared is useful. Can we understand something useful we treat as resource, right? Yeah. X squared is useful. So that's our resource. Okay? So when we calculate x to the fourth, can we use our resource x squared? Yeah, that's our resource, right? Our property. Yeah. We have the ownership. So we can use it. Yeah. So we apply another square using our existing resource. So after that, can we treat x to the fourth is also our resource? Yeah. Yeah. So all the way down, so everything we have calculated, we can treat as resource, right? Yeah. We just use our existing resource to save. Yeah. So the essence is we want to reuse the resource, right? We don't want to recalculate, right? Same expression, x to the 8th. Do you want to calculate it a second time? You don't want, right? Yeah. So that's why we want to reuse our resource as much as we can. Whenever you see x to the 8th, grab from your pocket, because you already have x to the 8th in your pocket, right? So grab from your pocket. When you see x to the 16th, you need to use x to the 6th. Do not recalculate it, okay? So grab from your pocket. Use it directly. You can save. That's the idea. That's this idea. Reuse the resource idea. Okay, all right. Yeah. So let's use this resource to do more saving. Yeah. All right. But this time, we release the restriction. We do not require n power of 2. We consider any n, any positive integer n. Yeah. Let me use a simple example. Concrete example, so we can see, we can work on it. Yeah. So we get more experience. Yeah. All right. Here, I choose n equals 217, this number. Yeah. I just pick, some random number. Yeah. But not too big, so we can work it out, right? If I pick, 6-digit number, too much work, right? I don't want to work on that big number. Yeah. All right. Now, when I work on it, I ask this question. What is the largest power of 2 under n? Power of 2, because I know how to use the minimum number multiplication to calculate that power of 2. N. Yeah. Largest power of 2 under less than 217. 128, right? Yeah, 128. 2 to the 7th. Because if you calculate 2 to the 8th, that's 256. Greater than 217. Yeah. So we use this 128. Yeah. 2 to the 7th, this power number. Power 2 number. In order to calculate 2 to the 128, how many multiplications do you need? In order to calculate that, x to the 128, how many multiplications do you need? This one. 2 to the 7, 2 to the 7, how many? 7, right? Yeah, because that exponent number, you just use this exponent number, 7. All right? 7 multiplications. Yeah. But think about, after 7 multiplications, what do you have in your pocket? You don't want to throw away your valuable resource, right? You need to keep them. That's your resource. Your resource pool. That's the pool of your resource. You maintain a pool of your resource, right? Yeah. You need to, organize. You need to do some bookkeeping on your pool of resource. Think about that. That understanding. Yeah. So the fastest way to get x to the 128, yeah, because you calculate all these power of 2, all these numbers, right? Yeah. Yeah. Can you treat all these numbers as your resource? Can you put them all in your pool of resource? Yeah, in your pocket. Yeah. Whenever you need any of them, you just grab it from the pool, okay? From your pocket, okay? Yeah. Let's use that understanding, right? Now, remember our goal, we need to work on n equals 217. That's our goal. Now, let's decompose that 217 number. Can we use power of 2 numbers to represent 217? Because power of 2, we can use the resource in our pool to represent. So now we want to represent the number 217 as a sum of power of 2. How about that? Sum of power of 2. Yeah. Can you do that representation? Yeah. Let's split. Yeah. First time, let's take out 128. So we have 89 remain. All right. Then we split 89. Right. 89 we split as 64 plus 25. 64 power of 2. Okay. The largest power of 2. 25. We take out the largest power of 2 from 25. That's 16, right? Yeah. And then 8, then 1. See, that's our decomposition. That is our decomposition of 217 number. Then, now we're ready to write our final expression. So x to the 218, this whole monomial, we can write a multiplication of these power of 2 expressions. Yeah. The first one, x to the 128 times second factor, x to the 64th. Yeah. The third number, x to the 16th. Yeah. Then x to the 8th. The last one, x. All right? Yeah. But when you use all these numbers, you do not need to do any new calculation, right? Yeah. Because you get them from your resource pool here. We also put x in our resource pool, right? Because we can use it directly, right? Yeah. All right? Yeah. So then, if you can use your resource pool objects, okay, then to form your final expression, how many more multiplications do you need? You still need to do some multiplication, right? But how many more multiplications do you need? How many dots, right? Each dot corresponds to one multiplication. 1, 2, 3, 4. 4 dots. That means other than the objects you pick from your resource pool, you still need 4 more multiplications. So the answer is 7 plus 4 equals 11 multiplication. 7 plus 4. To generate your resource pool, you need 7. Okay? After that, you need 4 more multiplications to get the final answer, x to the 217. So the answer is you need 11 multiplications to find x to the 217. Can you see that? Can you see that? Yeah. This idea, okay? Yeah. This understanding. Yeah. All right? Yeah. And another observation after we complete the calculation, another observation. Can you see this expression related to the binary expression of 217? Binary, yeah, right? The binary expression, right? Yeah. You know, the highest position, because this 1, yeah, because 7, 6, so 1, 1, but you don't have 5, right? 5, that's 0. 4, you have. 3, you have. You don't have 2, 0. Yeah, so you have that. So the binary, this is binary expression. 1, 1, 0, 1, 1, 0, 1. Can you see that from the decomposition? The decomposition corresponds to your binary representation. Okay? If you have the binary representation, then you can find decomposition easily, right? Yeah. one observation. Yeah. All right. Yeah. The general process. Because we only work on a special example, can we generalize this method to more arbitrary and, any number? Any number, can we use the same way? Yeah, we can. Yeah. Find the largest k. Yeah. Actually, you just do a binary representation first, right? So then you know how to write the decomposition. Yeah. All right. Yeah. So the largest, yeah, k multiplication. Yeah. Then, yeah, because the reason it's the largest is if you do another square operation, this number will be greater than n. That's why 2 to the k is the largest power of 2, less than or equal to n. Yeah. All right. Yeah. So which implies that, yeah, can you see n is less than or equal to 2 to the k plus 1 minus 1? First, you need to agree, is this inequality correct? Do you agree that? Yeah. Yeah. Yes, because we assume 2 to the k is the largest power of 2, less than or equal to n. So when you do another k plus 1, it will be greater than, strictly greater than n. Otherwise, k won't be the largest, right? You have a larger power of 2, less than or equal to n. Yeah. So you agree this inequality is correct, but this is a strictly greater than n, right? It's a strictly greater than n. 2 to the k plus 1 is an integer. One integer is strictly greater than another integer. Can we say the greater one at least one more than the smaller one, right? Yeah. All right? The greater is at least one more. If you subtract by 1, then it's greater or equal to n, right? Because the difference is at least 1. After you subtract 1, there is a possibility could be equal, right? But overall still greater. Yeah. Overall still greater. Yeah. All right, so that's the analysis, the logic behind it. Okay, all right. Then the binary representation, any n can be represented by power of 2, right? From the binary representation. Yeah. So here, yeah, and this number, because this number, you can use all the smaller power of 2. The sum of all the smaller power of 2 will be equal to this one. You can see it easily. You can see it easily. Okay? Yeah. One simple way to see it, if you move this minus 1, you add 1 both sides. Okay? 1 plus 1 is 2. 2 plus 2 is 4. Then 2 squared plus 2 squared, 2 to the 8th. Every time you add the first 2 numbers, that's the next number. First 2 numbers, that's next number. Then at the end, you use 2 to the k plus 2 to the k, that is 2 to the k plus 1. Yeah. So you can see that. All right. Yeah. You can see that. So this tells you that any integer less than or equal to this number can be represented by your resource pool objects. The object formula, because all these things in your resource pool, right? All these power of 2, x to the 1 of the power of 2 number in your resource pool. Okay? That means these objects is sufficient to represent any n number less than or equal to 2 to the k plus 1 minus 1. You just select some of the objects. Okay? Yeah. If you select all, you represent this largest positive number. Okay? So that understanding. That means use this method, you can always find the answer. It always works. So here we will just want to see if it sometimes works, sometimes does not work. So this analysis tells us this method always works. Okay. All right. Yeah. All right. Yeah. Elements. Yeah. So all. Yeah. You can always find a combination. Okay. To make it work. Yeah. All right. Yeah. Yeah. So here. Yeah. So let me move to the next topic. All right. C.4, repeated cubing technique. This time, can we change square to cube operation, right? Yeah. Similar. So we just do some analogy here. Change square to cube. We can get something new. Yeah. But the whole method, similar. We just do some adaptation. Okay? Yeah. All right. So to show you, let's still, yeah, because power of 2, this time can we consider the structure power of 3? Yeah. Power 2, power of 3, that structure. Okay? Yeah. Let's work on the same example, 217. But this time, we use power of 3 structure to split this number. Power of 3 structure instead of power of 2. Okay? Yeah. All right. What is the largest power of 3 under n? Largest power of 3 under n. Yeah. Yeah. Here, let me give you. Okay? Yeah. 3 to the 4th. Yeah. 81. Because 3 to the 5th, that's 240 something, right? 243, greater than 217. So the last one is 3 to the 4th, 81. All right. Yeah. The fastest way to get x to the 81st. Fastest. We want to calculate x to the 81st. How many multiplications do we need? The smallest number of multiplications do we need to calculate x to the 81st? 8, not a 4, all right? 8. Because 1 cube operation, you need a 2 multiplication. 1 cube operation, it's not a 1. A square operation, you need a 1. But a cube, you need a 2. So 4 times. You apply cube operation 4 times. That means total 2 times 4, 8. 8 multiplications. 8, 2 times 4. Okay? Yeah. All right. Yeah. Here I show you explicitly. The first cube, you need a 2, right? 2 dots. Okay? Next cube, another 2 dots. Okay? Yeah. Every cube, you need 2 dots. All right? Every cube, 2 dots. So the last one, you need 8 dots. That's 8 multiplications. Yeah. 1 cube, 2 dots, 2 multiplications. Okay? Yeah. 8. All right. Yeah. So reuse the resource. This is your resource pool, the pool of your resource. Yeah. You can reuse them. All right, yeah. Okay. All right. With 8 multiplications. Then decomposition. We want to decompose 217 as a power of 3. Use the similar method we did in the previous slide. Okay, all right. Yeah. But when we extract power of 2, remember the base is 3, right? power of 3. The base is 3. That means we represent this integer using base 3. Have you heard of the base 3 integer representation? Base 3. Base 2, that's the binary representation, right? Base 3, that's the ternary representation. Base 3 representation, the ternary representation, okay? But in the ternary representation, your coefficient could be 0, 1, 2, less than 3, 0, 1, 2, okay? That means you can use 2 copies of 81, right? When you extract power of 3 from the pool, you can use 2 copies of 81 from your pool. That object you use twice, okay? X to the 81st, you use it twice. How about that? You're allowed to use it twice. 2. So that's why 217, we take out the 2 times 81. Then the remainder is 55. Then from 55, we take the power of 3, but we can take up to 2 copies, okay? Up to 2 copies. Yeah. So 2 times 27 plus 1. Another 2 copies, okay? Yeah. Because our ternary representation, we are allowed to use coefficient 2. That's why we can take 2 copies, okay? Coefficient is allowed to be 2, all right? But in the binary representation, the coefficient is not allowed to be 2, right? Yeah. Only 0, 1. You cannot use coefficient 2 in the binary representation. So the ternary representation, we need to change a little bit, okay? All right. Then, our final representation, x to the 217, yeah. Now, x to the 81st times x to the 81st. Yeah. 2 copies. Yeah. So multiply. X to the 27th. Yeah. 2 copies. Yeah. Right? Yeah. So you have 1, 2, 3, 4, also 4 dots, but this time your total multiplication 8 plus 4, 12. 12 is 1 more than 11. We use the repeat squaring, we use 11 multiplication, right? So this one is not as good as the repeated square. Not as good as that one. Yeah, because we need 1 more multiplication. 8 plus 4, we need 12 multiplications. That previous one, repeated squaring, 11 multiplications. Yeah. All right. Which method the repeated squaring or repeated cubing performs better in general? To answer this question, sometimes repeated squaring better, sometimes repeated cubing better. Sometimes repeated cubing can do better than repeated squaring. Okay? Yeah. Here, let me give you a simple example because I want to convince you. Sometimes repeated cubing can do better than repeated squaring. So let me calculate a simple example to convince you. Let's calculate x to the 15th. Simple, right? All right. To use repeated squaring, how many multiplications do you need? First, let's generate our resource pool first. Oh, sorry. Okay. Too sensitive. What's that? Yeah. All right. Yeah. Generate the resource pool x squared, x to the 4th, x to the 8th, right? With 3 multiplication, right? Yeah. X squared, x to the 4th, x to the 8th. 3 multiplications. Yeah. That's all the resources we need. Okay? All right. After that, x to the 15 equals x to the 8th times x to the 4th times x squared times x. Right? Yeah. All right, yeah. 3 more, right? 3 dots, 3 more. Total 6 multiplication, right? 3 plus 3, 6 multiplication. Okay, all right. Now let me use repeated cubing. I want to show you if we can save some multiplications. Okay, repeated cubing. X to the 15th. Can we write it as x to the 5th times x to the 5th times x to the 5th, right? Yeah. When we calculate x to the 5th, when we calculate to the 5th, can we use x squared times x squared times x, right? Yeah. X squared equals x times x, right? Yeah. Look at, to calculate x to the 5th, we need 3 multiplications, right? X to the 5th, we need 3 multiplications, right? Yeah. Then x to the 15th, we need 2 more, right? Right. So total, we get a 5 multiplication. Sorry, 5. 5, is this 5 better than that 6? Yeah. So this example shows you sometimes repeated cubic can do better than repeated square. So we have, each side we have one example, right? One example, repeated cubing can do better. Sorry, repeated squaring can do better. One example, repeated cubing can do better. Okay? Yeah. So your answer, it depends, right? Yeah. Question. Take 4. That's by Horner's rule. Take 4, right? If we by repeated squaring, because when we need to reach x to the 4th first, right? You need 2 multiplication to get x to the 4th, right? Then 1 more, that's to the 5th. 2 plus 1, 3. You can save 1. If you use 4, you waste 1. You can do better. Yeah. X to the 5th, 3 multiplication, not 4. Okay? Yeah. Because you do 1 square operation, you can save 1. 1 square operation, save 1. All right? Yeah. All right. So we've completed the second topic. The last topic, let's see how much time. Oh, I have about 10 minutes. So let me start. The last topic I couldn't finish, but let me start a little bit. C.5. Take advantage of the structure of Pascal's triangle. So this one, we need to use a special mathematical structure. It's called Pascal's triangle. It's some interesting triangle, yeah? But that structure, very special, and it is useful. All right, so let's look at that special structure. All right. Now, we want to consider a special polynomial. It's not a monomial, special polynomial. Now, it's the last missing piece. Remember our question number 10 of the quiz? You need to choose a polynomial, right? Special polynomial. Here, we choose a special polynomial. Okay? Yeah, the last missing piece is here. Okay? All right. Yeah. But the coefficients here, n plus 1 coefficients, need to follow some special pattern. Okay? Not arbitrary coefficients. We need to consider some special pattern for these coefficients. Yeah. All right. What kind of pattern? Here, the pattern I want to talk about, Pascal's triangle pattern. Okay? So let me show you. This is Pascal's triangle. Yeah. That little triangle. Any of you has seen this before? Pascal's triangle. Okay. Top is 1. Then 1, 1. All right. Yeah. 1, 1. All right. Then you can see the next row always. The current number is the sum of two numbers on its shoulder of its previous row. Okay? Yeah. Always like that. Okay? This 4, 1 plus 3. 6, 3 plus 3. 4, like that. Okay? This everywhere is correct. Everywhere. Right? Yeah. Like that. Yeah. Right? Pascal triangle. Okay? Yeah. Very interesting. Yeah. Structure. Okay? All right. This Pascal triangle corresponds to another special structure here. It's called binomial formula. Binomial formula. Monomial, we know monomial, right? Yeah. But here, binomial, okay? Yeah. So binomial, x plus y, two terms inside parentheses. Then x to the plus y, this, parenthesis, raised to nth power. Raised to nth power. So there is a binomial formula. So this is a binomial formula. Okay? We use the combinatorial numbers. Okay? N choose 0, combinatorial number. N choose 1. All right? Yeah. N choose 2. All these combinatorial numbers. In your discrete math, you learn the combinatorial numbers, right? Yeah. Where you have M balls in your pocket. Yeah. M balls in your pocket. They look the same. Okay? M balls in your pocket. They look exactly the same. Every time you pick 2 of them, how many different ways you pick 2 of them? That's N choose 2. Okay? That expression. There is a formula. N choose K. N choose K, there is a formula. I will write it out. So the binomial formula gives you this formula. Okay? Is the binomial coefficients. Binomial coefficients. The combinatorial numbers as the binomial coefficients. All right? N choose K, this is a formula. Okay? N factorial over K factorial times N minus K factorial. The formula for N choose K. Yeah. All right. Yeah. So, and the Pascal triangle corresponds to binomial formula. In which way? Yeah. Row by row. Okay. Yeah. The first row, x plus y to the 0. Exponent number is 0. That's 1, right? Yeah. The second row, x plus y to the first. Yeah. Then the coefficient, x coefficient is 1, y coefficient is 1. That's why you see 1, 1 here. Okay? You see 1, 1. X coefficient is 1, y coefficient is 1, 1, 1. Okay? All right. Next row, x plus y squared. Okay? The coefficient, 1, 2, 1. Okay? 1, 2, 1. Yeah. Then next row, yeah. So let me erase this. Erase, you can see clearly. Yeah. Next row, 1, 3, 3, 1 corresponds to a coefficient of this binomial expression, x plus y to the third. 1, 3, 3, 1 coefficients. Yeah. And so on. Next row to the fourth. Next one to the fifth. Sixth. And so on. That's the famous binomial formula. People also call it Newton's formula. Newton discovered this formula. Okay, Newton's formula. Yeah. All right. Yeah. So let me look at the time I left. Oh, good. Still 5 minutes. Yeah. 5 minutes is probably enough to complete this slide. Now, we can make our conclusion. We can make our conclusion quickly. So what's that? All right. The question, how many multiplications do we need to calculate, here I use a special example. Okay, I give you a simple example to show you the point, the main point. The last missing piece, remember? I talked about that last missing piece, all right? Now, we want to calculate this special polynomial because the coefficients has some special pattern. There is some special pattern in the coefficients. Okay? Yeah. What that pattern? What that pattern? Look at, you can find the coefficients in the Pascal's triangle. See? Yeah. 1, 5, can you see it corresponds to this row? 1, 5, 10, 10, 5, 1. Right? Yeah. One of the rows in the Pascal triangle. It means it corresponds, this formula corresponds to x plus 1. Now, y, you take y as 1, right? X plus 1, parenthesis, to the fifth. 1 plus x, parenthesis, to the fifth. Is it that structure? Yeah. Yeah. If you apply Horner's rule, you need 4 multiplications, right? Not 5, 4. Because leading coefficient is 1. Okay? The leading coefficient is 1. Last multiplication you can save. You don't need the last multiplication, right? The last one you can save it. So the Horner's rule, you need 4 multiplication. Okay? All right. Now, Pascal's triangle. Yeah, because we identify this polynomial corresponds to one row in the Pascal's triangle. That means this polynomial can be represented as parenthesis x plus 1 to the fifth. Now, you tell me, to calculate x plus 1 to the fifth, how many multiplications do you need? You don't look at addition. You ignore addition. Only look at the multiplication. How many do you need? Let me ask this. How many multiplications do you need? We calculate this. We just did it before, right? Kirill, your question. What's the right answer? X to the fifth. 4, but we have an improved version, right? Yeah. Right, we use the improved version. Yeah. Not, yeah. 3. Okay? To calculate x plus 1 to the fifth. 3. The first one, x plus 1 times itself. Right? The second one, square times itself. All right? The third one, x plus 1 to the fourth times x plus 1. 3. You can see we reduce the number from 4 to 3 if we use the Pascal's triangle knowledge. Reduce, right? Yeah. Now, back to that last missing piece. Can we consider x plus 1 raised to a very large number? Raised to some special number? Yeah. Connect, okay? Question number 10, connect to the slide. All right? All the missing pieces are there. All right? All the missing pieces are there. Okay? Yeah. But you need to connect the dots. Okay? Yeah. So your logical reasoning, you need to connect several dots in your logical thinking, okay, yeah, to complete, the whole justification. All right, yeah. All right, that's it. Yeah.